Mute, start video. So let's see, we can start the class now, I guess. Let me see where we were. We were up to homogeneous first order ordinary differential equations. Somebody might, however, have a question or a request or would like me to deal with a particular subject. First of all, can you see the screen? We had a problem with that last time. So would people tell me if you can see the screen or not? Yes, okay. Oh, somebody, yes, we can see. Okay, example 7.5. All right, if someone would like to see me do that example, then why don't I do that? Where is 7. Wow, boy, we are really way back here. Okay, let me, I forgot to connect the iPad, so let me do that. This thing keeps getting disconnected. All right. So I'm connecting the iPad and I need to, I am so sick of seeing my feet. Let's see, where the hell is QuickTime? Oh, there it is, okay. QuickTime, new movie, iPad. Can we get the goddamn feet? Okay, so let's see if I can 110 on that. Let me just write 110 down. Let's go to notes, and why don't we make this a new note? Okay, so we've got a new note now, and what we're looking at here is Maxwell's equations in empty space. So we have that Gauss's law becomes very simple. It's just del dot E is 0. Del dot B is always 0 as far as we know. The curl of E is minus B dot, and C squared curl of B is E dot. So these then imply the wave equations, which are these wave equations, which are separable in rectangular, cylindrical, and spherical coordinates. Well, clearly they're already separated in rectangular coordinates. And the exponentials, these exponentials work. Actually, you don't need anything as sophisticated as this to get this to solve this equation. When I did, when we use B to be of this form and also say that K dot epsilon vanishes, then what we've done is we've jumped to the Coulomb gauge. But let's first try to maybe do this exercise. Okay, I've also had another question here. Let me first, though, get the, let's see, we're talking about, right, this is, I think, Okay, I'm going to look up the solution to this so I don't waste anybody's time. Okay, well, basically, what we do is we start with the equation that the curl of E. Now, once again, I've got this problem of, does anybody know how to get this to go to sharp as opposed to just this stupid version that well, anyway, all right, let's just look at the curl of E.
Dr. Cahill, we can't see your notes page.
Okay, right. So let's see where that is. Hold on. All right, I need to move it over here. And then I need to do that. And let me also disconnect the. Oh. Okay, so we have the curl of E is minus B dot. And as I said, I'm sorry about the pen. So now let's take the curl of that. So the curl of E will then be minus the curl of B dot. On the other hand, we know what B dot is, namely that B dot is from this equation, B dot is minus the curl of E. Oh, well, good thing. I'm sorry, I've already used that, so that was kind of stupid. So let me see if I can sort of undo those steps. Okay, now so let's see, let me just try to get this. So this is equal to, but I must say I don't immediately see why. Oh, well, that's obvious. It's the last equation here. So we're using the last equation. So we have curl of B dot is then E double dot over C squared. So we now have that expression. And well, this, then we use the identity for the curl. And remember.
Dr. Cahill, the whiteboard is behind the book.
Thank you. So now what we do is we use the fact that the curl of E is actually the gradient of the divergence of E minus the Laplacian of E. And Laplacian of E is simple in rectangular coordinates. You just hit EX, EY, and EZ separately with the Laplacian. And so now we have this expression. On the other hand, the divergence of E is 0 because we're in empty space. And so what we have then is that this is just minus, whoops, well, all right, grad squared E. And now we combine, let me do it with red, we combine these two equations, and that says then that E double dot over C squared minus Laplacian of E equals 0. And so that's the wave equation, or equivalently Laplacian of E is E double dot over C squared. Now, if you do the same thing, but sort of interchange E and B, you wind up with the other equation. So do you guys want me to do that, or is that sort of obvious? Anyway, you do the same thing. In other words, you start with the curl of B, and you then use the fact that the curl of B is E dot, and so this is the curl of E dot over C squared, and then the curl of E is minus B dot, and so this is equal to minus B double dot over C squared. And you then use the identity for the curl of the curl. You express it as the gradient of the divergence of B minus the Laplacian of B. This is always zero as far as we know. And so now what we have is we combine these two equations. In other words, this is actually just minus Laplacian of B. Well, I've got the colors all confused. But in any event, what we then get is that B double dot minus Laplacian of B equals 0. Okay, so that's 7.5. Now, in chat, there was a question about problem 634. So let me see what 634 is about. Right. Well, this is the one I discussed yesterday, and I gave a hint for this. It's that it's basically what we're dealing with here is we've got the theta of y. So this is the so this is equal to 0 for y less than 0 and 1 for y greater than 0. And so what you want to do then is, I would say you just use, all right, let me give you another hint. Assume that this is the right answer. And so just compute 1 over 2 pi I, integral minus infinity to plus infinity of e to the I y x dx over x minus I epsilon. Do that for these two cases. Do it separately for the case y less than 0 and for the case y greater than 0. And then you obviously add a ghost contour, and you put the ghost contour where you have to put it in view of what y is, whether it's negative or positive. Okay, so that's that one. In fact, I think I've almost done the problem for you. Is there another question, or shall I just go to where I intended to start? All right, well, let me start here. Remember, we defined homogeneity by saying that a function's homogeneous if you scale all the variables in the same way you wind up scaling the function by a power of the scaling factor. And so we're assuming then that we're looking at a first order ODE of this form, PDX plus QDY, and assuming that P and Q are homogeneous of degree n. And so then the trick is to change variables to let, what you do basically is you turn X into the scaling variable. So you let Y equal XV, and then this becomes the differential equation, except now dy, since y is xv, dy is xdv plus vdx. So now this is our differential equation. And you then use the homogeneity of degree n for both P and Q to rewrite this as that and this as that. And once you've done that, you've got a separable differential equation, and dividing through by, I guess, px to the n, and a little massaging, you get it into this form. Let me get rid of this stupid thing. You get it into this form, and once it's in this form, you integrate both sides, and you get an integration constant here. And this gives you x as a function of v, or v as a function of x. And once you have v, y is xv. So that's how it's done. And as an example of that, here's a differential equation in which p is x squared minus y squared, q is 2xy. They're both homogeneous of degree 2. So you let y equal xv, and that becomes this expression here. X squared cancels out, and you have this expression. You then divide by x times 1 plus v squared, and you get this equation. You get something, well, what you get at that stage actually is you get dx over x plus 2v, let me see, I might have been going a little too, right. You get 2v dv over 1 plus v squared. And now you can integrate those two. You integrate these two, and you get this equation here. And so that says log of x is log of 1 plus log of 1 plus v squared is log of some integration constant. And well, that just tells you that x times this is another constant, well, is c actually. And so then remember that if you multiply both sides by x, you get x squared here, but you get xv squared, but xv is y, so you have 1 plus y, x squared plus y squared is cx, and you solve like that. So that's how that works. Now, linearity really makes things simpler. Whenever things are linear, you may not be home free, but you're in much better shape. So I'm going to make myself a coffee, but why don't you guys look at this for a moment, and I'll be right back. So what we've got here is a general linear first order differential equation. It's inhomogeneous if S is non-zero. And the nice thing is that because the equation is linear, it's possible to find an integrating factor, and the integrating factor turns out to be pretty simple. So what we do is we multiply the differential equation by alpha, and we then get this equation. And now we see that we've got that P is this term, and Q is just alpha. And so now we want to require that that alpha be such that the equation in this form is exact. And so that means that it's the differential of something. So this thing here has to be the x derivative of something. This has to be the y derivative of the same thing. But then what you know, since the double partial derivatives don't care about the order, you get py has to be q sub x, and py is very simple. It's just alpha r. Qx is just alpha x. And so now you have the equality of these two things. So that's a differential equation. Alpha x over alpha is r. And this thing is the x derivative of the log of alpha. And so that's this expression, which we can then exponentiate. In other words, if I just fill in a step here, we've got, so d log alpha dx is r of x. So that means that log alpha of x is an integral r of x prime, say dx prime, up to x, apart from, well, let's say from x0. And this is this minus log alpha at x0. So it's these two is equal to that. And so this is log alpha of x over alpha of x0 is this integral x0 to x of r of x prime dx prime. And so then we exponentiate both sides and we get alpha of x over alpha of x0 is e to the integral x0 to x, that's a 0, x0 of to x of r of x prime dx prime. And that gives us this equation. So we found the integrating factor. And so now that we've got the integrating factor, what we can do is we have alpha r is alpha x. And so the original differential equation, which was yx plus ry equals s, when you multiply that by alpha, what you have is alpha yx plus alpha ry is equal to alpha s. And now on the other hand, alpha r is, I'm sorry, alpha, I've got this backwards or something. Alpha r is alpha sub x. So this is alpha sub x. In other words, the x derivative of alpha. That was the original, that's this equation. Alpha, the x derivative of alpha is r times alpha. And so we replace alpha r by the x derivative of alpha. But this is the x derivative of the product, alpha y, is equal to alpha times the source function or the inhomogeneous term. And so now we can integrate this equation. We get alpha y at x minus is equal to alpha y at x0 plus the integral, the definite integral of alpha s. And then dividing by alpha, we get this as the solution of the differential equation. So we've solved for alpha as this, That's the integrating factor. And now here we have the final solution. So that's the general solution of this kind of a differential equation. And if we now substitute for what alpha is, remember alpha is this exponential, and here we have alpha of x0 over alpha x. So this is this thing upside down. So we have a minus sign, and then that multiplies. In other words, 1 over alpha multiplies both factors, and so we have this expression here. And now what we can say is that the prefactor times y of x0 is actually the general solution of this homogeneous equation. Because this homogeneous equation would be, this is sort of the y derivative, the x derivative of y, of log y is equal to minus r. And so we go through the same razzmatazz and we get that. Then this is a particular solution of the inhomogeneous equation. And so this gives us the general rule that the general solution of an inhomogeneous equation, the general solution of an inhomogeneous equation is the general solution of the associated homogeneous equation plus any old solution of the inhomogeneous equation. Would somebody, is that okay, or should I do a little extra on some aspect of this? As I said, we've got this swamp cooler that's super strong, and it's now freezing in here. So I'm putting on my Biden sweatshirt. Oh. Okay. Now, why were we able to do this? We were able to do this because the equation was linear. And on the other hand, we could set P and Q, we could do these simple things. When P and Q are more complicated, the integrating factors are much harder to find. Now, here are two examples. This is somewhat amusing, actually. Maybe I should do this. If you, the downward speed of a mass m in a gravitational field of constant acceleration is described by this differential equation, in which b is a factor representing air resistance, and v is the velocity, of course, m is the mass. And of course, b is huge if the falling body has a parachute. Damn this thing. And this equation is like the earlier one, and the difference is that t is the independent variable, r is just a constant, and s is another constant. And so if you apply the rule here, what you get is this solution. Maybe I should do that because it's sort of amusing. So r is b over m, and so let's see, maybe I should get alpha first. So, well, maybe I'll just go to the final solution. So in this case, it is v of t would be equal to e to the minus an integral t0 to t of r, and r is just b over m dt prime. And now we multiply that by v of t0, and we plus an integral from t0 to t of, and now this is the same thing as the other thing, as the other case. And so this is e to the b over m, and it would be t prime minus t0, I think. And what's s? S is g, dt prime. Well, this gives us another exponential, and this is an exponential, so this is e to the minus b over m t minus t0 times v of t0 plus g e to the, well, let me do it slowly, e to the minus bt0 over m, and now I'm just integrating e to the minus, e to the b over m t, and so this is going to be e to the b over m t minus t0, but there's a factor m over b. Okay, well, let us hope that that I actually did this correctly, because the answer here is before us, namely it's an e to the minus b over bt over m times a factor here, and then this factor here. So this is the terminal velocity, because when t gets big, this term vanishes. And it's 200 kilometers per hour for a falling adult. A diving falcon can get to 300 kilometers per hour. And it turns out to be like the speed of a falling bullet. On the other hand, mice can fall down mine shafts and run off unhurt, and insects and birds can fly. So what we've got here is this ratio m over b. As this m gets small compared to b, then you get that this quantity here becomes small. And we can see that actually from an old argument. Suppose the density of organic matter is rho, then the mass is proportional to the cube. On the other hand, the air resistance is proportional to the square. So this is rho r, and this goes to 0 as r goes to 0. R being the diameter of a man on the one hand, or an insect on the other. And so if you go from, let us say, 1 meter to 1 millimeter for a tiny insect, that's a factor of 1,000. So you've gone from 200 kilometers per hour to 200 meters per hour. And well, that's not falling at all. That's why insects can easily fly. A little flapping of the wings and you're home free. And if, of course, the falling bodies are microscopic, then what you do is you switch to statistical mechanics, and you get a distribution in equilibrium, which is e to the minus the potential energy, mgh, divided by the kinetic energy, the thermal energy, kT. Okay, I'm going to skip that one, and I'm certainly going to skip that one. Next Wednesday, if you guys want to see that, ask me. Now here comes small oscillations. This is very important in physics. And it just explains an enormous amount of, I mean, the examples of small oscillations are just everywhere almost. Let's suppose we have, in this case, we have n particles in three-dimensional space, and I've given them all different masses, which makes the thing a little bit more complicated. But a single potential U of X, but of course, X depends upon 3n variables. And now I rescale the X's in order to have a common factor here. I don't know how necessary this is. I one day thought it was important, so I did it and haven't changed since then. When we make that scaling, we can then define V of Q as U of X, and then we get this expression here, which is very simple. It's m over 2, the dot product of the velocity of the system minus the potential energy is the Lagrangian. And the corresponding Hamiltonian, remember, PI would be MQI dot. And we then get this as the Hamiltonian. It's conserved because the Lagrangian does not depend explicitly on time. And let's suppose then that the V of Q has a minimum somewhere and at Q0. And in this case, then at low temperatures, or if we start it near Q0 and don't give it too much of a kick, it's going to be, the system is going to be sitting near Q0. And so if we expand the potential near Q0, letting Ri be Qi minus Qi0, we then have this as the Lagrangian. In other words, the approximate Lagrangian for when all the particles are near the minimum of the potential has this form. And we can call this V double prime, the matrix of second derivatives. But now we learned back in chapter 1 that if you, first of all, this thing is real because the potential energy is real. Secondly, it's symmetric because the JK derivative is the same as the KJ derivative. So it's a real symmetric matrix. That means it can be diagonalized by a real orthogonal matrix. And if we call the new coordinates S, these again are the coordinates from the minimum, but now rotated by the orthogonal transformation, we get this expression here, and we've diagonalized V. And so now Lagrange's equations are super simple. They're just m, the double time derivative of SI is minus SI times the ith diagonal element of the diagonalized potential. These things are then called normal modes, and for good reason, physicists love them. They're just uncoupled harmonic oscillators, and for given initial conditions determined for the ith oscillator, which determine AI and BI, one gets this as the behavior of SI. And remember, SI is really a linear combination of all the displacements, which are Qi minus Qi0, and the Qs are scaled actual distances. All right, well, that was a huge mouthful, but, and to tell you the truth, I should invent a nice example for this, because it is so very important. But it's in other words, if you have any quantum mechanics problem in, say, 1 or 3 or however many dimensions, and again, for the case in which the potential is bounded below. So this doesn't apply, for example, to the hydrogen atom, because the potential for the hydrogen atom, let me switch colors here to maybe blue. So the potential of the hydrogen atom is minus 1 over r, or e squared over r in some units. This is not bounded below. This does not have a minimum. But if you have any other problem, not any other problem, but many problems, you will have some minimum of the potential V. And so what you're going to have is small oscillations about that minimum. And so then what do you know? Well, what you know is approximately the energy levels of just harmonic oscillator energy levels about that minimum. In other words, getting back to the Hamiltonian, they're just of this form, and about the minimum, then it's just again the harmonic oscillator. And so that's why the harmonic oscillator is so important. It's important because it's simple, but also because the applications are everywhere. So remember, we have a chat function. You guys can use it. You can shoot me a question, and you can do it anonymously. In fact, you should do it anonymously because you know, we have the best Congress money can buy. All right, let me switch now to something that's that we wouldn't talk about, 80 years ago or 100 years ago, but we can talk about now because of the availability of high-speed computers. So let's look at a system of n first-order ordinary differential equations. And so we have x1 dot is f1 of all the x's, x2 dot is f2 of all the x's, xn dot is fn of all the x's. This thing is said to be autonomous if the functions are independent of the time. And these systems, autonomous systems, are very, very general, and they can even represent functions that do depend upon time and functions that aren't first order. You see, these are n first order equations. This can represent a higher order system. And moreover, especially when you have it in this form, MATLAB can solve it for you. And you can have a lot of fun with that. And I urge you to, in fact, do that. So what do we have? So let's suppose we want to make a time-dependent system of n equations. Now the time derivative, the functions f have a t in them explicitly. What do we do to write that in this autonomous form? Well, we just set t, we just call t xn plus 1. And so then this thing becomes f of x1 through xn plus 1, and so forth. But now what about xn plus 1? Well, xn plus 1 is the time derivative of xn plus 1, but xn plus 1 is t. The time derivative t is 1. So this becomes very, very simple. So for example, suppose we can set x equal to x1 and t equal to x2. And by doing that, we can turn this explicitly time-dependent differential equation into a simple autonomous system where x1 dot is minus x1 cubed, that's this, but now this is sine cubed of x2, and x2 dot is 1. So this is now an autonomous system of 2 first-order ordinary differential equations. We can, a similar trick can be used to turn a system of n higher order differential equations into a system of more than n first order differential equations. And for example, if we set x1 equal to x2 dot and x2 equal to x1 dot and x3 equal to x, we can turn this equation into, well, x1 dot, that's x2, I'm sorry, this thing is x triple dot. Well, that's x3, let me get this straight. This is x3 triple dot. Well, x3 is x. So if we want to translate this, what we have is this one becomes that, that's for sure. X dot, we said, was, now I'm getting confused here. I hope I did this right. Certainly x2 dot is x1 and x3 dot is x2. Actually, I may have screwed this up. So x. All right, look, let me think about that. I've just, there may be a typo or something here. I will fix this and send you an email about it. Let's do it that way. Here's an example, which I hope is correct. Here is a second order nonlinear, two second order nonlinear differential equations. And by setting x1 equal to x dot, x2 equal to y dot, x3 equal to x, and x4 equal to y, I claim that we can turn this thing into this first order autonomous system. And here's a trajectory. And so this is one I use MATLAB to solve it. This is a trajectory of x of t and y of t. Those are the points. And for this system, for the time interval from 0 to 400, and I chose R equal to 0.2, A equal to 10, B equal to 10, G equal to 1. Initial conditions for x0 and y0 both equal to 5. So they basically started, I started basically here, and I gave it I started moving like this. X dot is 10, but y dot is 0. So it was moving horizontally here at time 0. And the scripts are, the MATLAB scripts for all the figures in this chapter are in a particular folder at GitHub. They're in the Differential Equations folder at GitHub. By the way, that's something I haven't mentioned here before, maybe because it hasn't, well, I don't know, it just didn't occur to me. But I put all kinds of MATLAB scripts, Fortran programs, and so forth on GitHub, and you can just go there. It's publicly available, and look at this stuff. What I haven't yet done, and I've been putting this off now for a couple of years, is that I should have a file in each folder telling people what the different files are and what they do, and I just haven't done that yet. I should. Anyway, this is rather complicated behavior, and I mean, MATLAB generated this in, seconds. fact, it might even have been less than a second. Now, there's a question here. Is that substitution for t related to doing a u substitution in integration? I have no idea what that means. So I'm sorry, Honest Abe, I do not understand the question. And that's probably because I didn't notice the chat until, so let me put these chats a little closer to where my eyes normally focus. So I don't remember what substitution for t. Okay, exact higher order differentialization. Well, obviously, if you have an equation of this form, which is a total derivative, you can call it exact. And that's a standard definition, and that's an example of doing it. Another case that's soluble is a constant coefficient differential equation. Here's one like this. Now, of course, this is the sort of thing that one could do with Green's functions also. Okay, well, here's a clarification of the question. You did a substitution for the first page of this, t equal to x2, t equal to, I think that was here, wasn't it? Yeah, right, t equal x2. I'm wondering whether that kind of substitution, when you're doing a substitution, I don't know. I don't understand the statement when you're doing a substitution for integration, so I don't know what that, I don't quite understand your question, but this is amusing. I mean, this plus MATLAB is really amusing because, I mean, I did something here, but you can take your own, you can write your own first order autonomous system and ask MATLAB to solve it for you, and you might find something amusing, and it's just a whole area of mathematical physics that's become accessible because of the availability of fast, cheap computers. Okay, so we've done that. Now, if this is a constant, if these are constant coefficients, a simple way to solve it is to set y equal to e to the zt. And if you do that, when you differentiate y k times, you just get z to the k, e to the zt. You factor out the zt, and then you just have a polynomial equation in z that will have n roots. In general, unless there's some funny symmetry, these roots are going to be different. And so then for each root zi, you have a solution y of t is e to the zit. If some of the roots are the same, then what you can do is it turns out that if you have, say, one root that occurs j times, where you can use these solutions. I suppose z prime is the root that that's degenerate. Then you use the functions y equal to e to the z prime t, y equal to t to the z prime t, and so forth, until you get even y equal t to the j e to the z prime t. So that's what you can do there. All right, I think we'll skip them and maybe go to this point, which is singular points of ordinary second order differential equations. And so basically you've got the second derivative is some function of the independent variable the dependent variable and the first derivative. And if, and you can call this, I'm calling this the acceleration. So if the acceleration is finite for all finite y and y prime, then we say that x0 is a regular point of the ordinary differential equation. If on the other hand, it's infinite for finite y and y prime, then we say x0 is a singular point. The key thing here is what typically happens is that for some singular value of x0, y double prime is infinite no matter what you choose for y and y prime, except for special cases. So let's look at the second order ODE, ordinary differential equation, y double prime plus py prime plus qy equals 0. It's linear and homogeneous. And if p and q are finite, well, then y double prime is always going to be finite for finite y and finite y prime. On the other hand, if these guys are infinite, then we've got a singular point. And now the mathematicians or applied mathematicians distinguish among singular points. So basically, if P or Q diverges as X approaches the singular point, but the singular point is no worse than a pole of first order in P and second order in Q. In other words, if X minus X0 times P and X minus X0 squared times Q remain finite as X approaches the singular point, then we say it is a regular singular point or a non-essential singular point. And these are the nice cases. And so basically, if your differential equation has no singular points or only regular singular points, you've basically got a nice differential equation. On the other hand, if either one of these diverges as X goes to X0, then we say that it's an irregular singular point or an essential singularity. And now the question is, well, what about as you let X go to infinity? When X goes to infinity, you'd expect that P of X and Q of X might become infinite, and therefore the acceleration would become infinite. So what people do, and of course the people don't want to talk about, don't want the variable to be that they're talking about to be infinite. And so what they do is they set z equal to 1 over x. And then the deal is if 2z minus p time of 1 over z being x, divided by x squared and q of 1 over z, which again is x, divided by x to the fourth, remain finite as z goes to 0, then we say that x0 equal to infinity is a regular point. They don't remain finite, but with if the second power diverges, but the first power doesn't, and here the fourth power may diverge, but not the second. As z goes to 0, then we say x0 equal to infinity is a regular singular point. Otherwise, it's irregular and essential. And an important example is Legendre's equation. You can write Legendre's equation in many forms, and if you write it this way, it's said to be in self-adjoint form. And you can then write it in non-self-adjoint form like this, or indeed like that. And now when you write it like this, you see it's got singular points at x equal to plus or minus 1 because you've got poles here. On the other hand, these are regular singular points because if you factor 1 minus x squared to 1 minus x, 1 plus x, you see that they both are only simple poles, so that means it's a regular singular point. Now, Frobenius figured out many years ago that one could form power series solutions of differential equations of a second order linear homogeneous ordinary differential equation at any of its regular or regular singular points. And so what we're going to do to analyze this is we're going to set little p equal to x times big P and little q equal to x squared times big Q. And we're going to assume that P and Q are polynomials or analytic functions. And we're going to assume that x equals 0 is either a regular point or a regular singular point. So we're going to choose to expand around x equal to 0. That's why 0 is here. And if x equal to 0 is a regular point or a regular singular point, or equivalently an inessential singularity, then we can say that P of 0 is finite and Q of 0 is finite. Okay. And now we're going to, this differential equation, if we multiply by x squared, we see that we convert big Q to little q, we convert big P to xp, and we get a factor of x squared out there. So this is our differential equation. And we're going to expand y as a power series in x about the origin, y equals 0. So we're going to look like this. This R, you notice, is as we write it here, it's not really defined. But the next thing we say is we say that x0 is not 0. So in other words, the lowest, the expansion of y about the origin, x equal to 0, has as its lowest power x to the r. It's the rth power. So in other words, the near x equal to 0, y is equal to a0 x to the r. And then the other terms are a1 x to the r plus 1 and so forth. So now what we do is we're going to assume this form. We're going to take this thing and shove it into this differential equation. And so to do that, we compute y prime and y double prime. We'll differentiate that, and we get two terms because we get one term rx to the r minus 1, and then we get n x to the n minus 1 plus r. And in both cases, we get this expression here. And now if we differentiate that, again, in fact, the easy way to see this, by the way, is to write this as a sum a sub n x to the n plus r, and then you see you immediately get this expression. Now you take this expression, differentiate it again, and you get r plus n times r plus n minus 1, a sub n x to the r plus n minus 2. All right, so these are our three formulas for the function y and its first and second derivatives. We take these three formulas and we put them into here, and then we get this expression. It's a sum a sub n x to the n plus r, and one of the terms is then a sub n, and that shows up here. I must say, I don't see quite where, that's multiplied by x, that's multiplied by q. So we've got that multiplied by q. So that's the term that I'm talking about here. So then this is the first derivative term, this is the second derivative term. So this term is x squared y double prime. These terms are xp y prime, and these terms are qy. And now if this is to be satisfied for all x, then the coefficient of every power of x must vanish. And the way you see that, of course, just in case someone, so let me switch to, let us say, red. The way we see this is what we've got there is a sum, and let me just call that, this thing is some sort of a power series, and I'll just call it beta sub n x to the r plus n equal to 0. And in order to see that all the betas have to be 0, we're summing here n equals 0 to infinity. We first we just set x equal to 0, so set x equal to 0. And everything vanishes except beta 0, so that tells us that beta 0 is 0. Then we take the first derivative of this, and when we take the first derivative, we get a sum beta sub n r plus n, that's an r plus n x to the r plus n minus 1. And now we're summing from n equals 1 to infinity. Now, once again, we set x equal to 0. If we set x equal to 0, the lowest order term here is beta 1, and that one has to be 0, and so forth. So, etc. That's how you do that. So, so in other words, the next step is you take a second derivative, and then you have a sum n equals 2 to infinity beta n. You have r plus n minus 1 times x to the r plus n minus 2. Now you set x equal to 0, and the lowest term is n equal to 2, and you get that one equal to 0. So let me make sure I've got this exactly right here. I think actually I shouldn't have done that. I should have said that one, because I think what one does is one differentiates maybe r times. Take this equation, differentiate it r times, and then you'll have, all right, so let me do it again for you. So we have here sum beta to the n x to the r plus n equals 0, n equals 0 to infinity. So that's our initial equation. Differentiate that r times, and then what we'll have is a sum n equals 0 to infinity, and we would have r plus n minus 1 dot 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 r plus n, I guess minus r, right? Or is it minus r minus 1? Minus r plus 1, I think. And we would then have beta sub n x to the n equal to 0. All right, now you set x equal to 0, and you get beta of 0 has to be 0. Then you differentiate again, differentiate this expression again, and you get an expression like this, n equals 0 to infinity, r plus n dot dot dot. Now the lowest term here was n plus 1. The lowest term this time is going to be n, and you would have beta sub n x to the n minus 1. And once again, you said you said x equal to 0, and the lowest order term, it's now not actually over here, the lowest order term. You see, since we've, what am I saying here? Actually, this term, it's actually beta. I shouldn't have called it beta sub. Let me call these beta sub r plus n. And so if you set this equal to 0, what you then get is beta, and you don't get beta of 0 is 0. You get beta of r plus n is equal to 0. Then, as I said, you differentiate, and now this is, I call this r plus n. Now set x equal to, this is all 0, set x equal to 0, and you get the n equal to only the n equal to 1 term, and so this is beta of r plus 1 equals 0, and this one was beta of r. Right, beta of r equals 0, sorry. Anyway, then you differentiate again and you get beta of r plus 2 equals 0, etc. Okay, so I don't know, it's obvious, but I mean, it's obvious if you look at it the right way, but obviously I can screw it up given enough time. So let's see, there was a question here. Can we do example 736 on Euler equations? How about if we do that tomorrow? We do that next Tuesday. Whoops, the internet connection is unstable. Now that's not very good news. But let me finish this, okay? As I said, you then get this expression, and so each of those square brackets has to vanish because it's a different power of x. And in particular, the lowest order one is when n is equal to 0. And now substitute n equal to 0, you get this expression here. That, and then since a0 we said was non-zero, we get that this is equal to 0. This is called the indicial equation. And it's quadratic, so it has 2 roots somewhere in the complex plane. And to analyze how higher powers of x, what we do is we expand P and Q as power series about the origin, where P0 is P of 0, Q0 is Q of 0. And then if you take these two expressions and then what you find is that in other words, you take these two expressions and substitute them in here, and then ask that every power of x vanish, you then get a more complicated recursion relation. So this is rather complicated, I completely agree. On the other hand, in the equations that we normally play with and like are ones where P and Q are very simple polynomials of low degree. And then the solutions are, then this recursion relation becomes much simpler than that. And when R1 and R2 are complex, then, so we're talking about the roots of the indicial equation. So in other words, the original solution here would be, R would be complex. So then what we would have would be a complex solution. We'd have two different real solutions, and they'd be the real and imaginary parts of a complex solution of the differential equation. So as I said, this nightmare recursion relation becomes much simpler if you have a simple differential equation. And two important examples are sines and cosines and Lagrange's equation. Is it, no, Legendre's equation and Hermite's equation and the hydrogen atom. So I think I'm going to redo this whole section because the Frobenius method is very important. It says basically, if you have a second order differential equation that's linear, then at least linear in y, then you can solve it by expanding about a regular point or a regular singular point. Okay, we're over by 1 minute. I think I'll stop, and I will try to do example 7.36 next time. And just to, damn that thing, just to remind ourselves, 7.36, which example was that? Okay, right. Well, in this case, apparently we have one root that occurs 4 times. I'm a little puzzled as to whether that's actually the case looking at it. So it's a good thing you asked that question, because conceivably there's a mistake in this. I'll have to look at that, excuse me, more carefully. All right, so I'm gonna, if there's an emergency question, let's answer it. Let's ask it right now, and I will try to answer it. Otherwise, I will wish you a good, safe weekend. And remember, because the temperatures are dropping, people are turning off their swamp coolers. The swamp coolers are no longer, when they're turned off, they're no longer ventilating the houses and the buildings and the places of business. And so there's much less ventilation as the temperature drops. And then as we go into winter, people are going to start shutting windows, shutting doors, turning on the heat. No swamp cooler at all, very little ventilation, and people are going to be infecting each other because these virus particles just hang in the air, kind of like molecules. They're bigger than molecules, obviously, but they're a lot smaller than insects, and so they just hang in the air for hours. And you're in a bar with one infected person, and he or she coughs, and you've got 1,000 virions that start floating around in the air. And of course, they float very slowly, but they hang around, and somebody else coughed 3 hours ago. And so the whole air in the bar is going to be, you're going to have virions everywhere, and you know, lots of people are going to get sick. So try to wear masks and when you're near other people, and try to stay away from other people. All right, goodbye, everybody. Sorry for going on and on and on. Have a nice weekend. So I'm going to stop the